Welcome to this video in which we will look at finite differences, so that by the end of this video you will be able to link finite differences to the definition of derivatives that you have learned in calculus. So let's look at finite difference approximations, and let's go all the way back to the definition of the derivative that you have learned in calculus. So we have a function f of x, right? So we draw x on the horizontal axis and the function values on the vertical axis. And shown here is just an example function that is graphed. Now from calculus, we know the definition of the derivative, that the derivative of this function f of x with respect to x at a location x equal to a, also written as a shorthand as f prime of a, is defined as, well, the slope of the line at this point a, f of a. Now in calculus, this is defined as the limit of x going to a of the difference of f of x minus f of a divided by x minus a. So that means if we start out with some arbitrary point x, and at that location we can evaluate f of x, then this ratio is basically the slope of the line that goes through the 2 points f of x and f of a. That's this ratio here. Now, the derivative is defined as the limit of x going to a. So we have to move this point x ever closer to a. And from calculus, we know we would have to move it all the way over to a itself to then be equal to the derivative. And you can graphically see that the slope of the line that goes through these 2 points, f of x and f of a, starts to become closer and closer to the tangent line slope at f of a. Okay, so it comes ever closer the closer we get. But unlike in calculus, we cannot take the limit all the way of x going to a because we only have discrete points available, a finite number of points at discrete locations of x. So then the task becomes, how do we find the derivative at some point xi? So here is that sketch again. Let's say I'm interested in the derivative at a point x sub I, with the associated function value f of xi. That would be the analytical derivative, the slope or the tangent, the slope of the tangent line at this point. Now let's go back to the definition from calculus, and I'm going to move my second point x as close as possible to the point where I'm interested in the derivative. And the neighboring point, the closest point, would be to the right, x sub I plus 1, where the subindex indicates that this is the next point. So then going back to the definition from calculus, I can approximate the derivative at xi as f of xi plus 1 minus f of xi divided by that distance xi plus 1 minus xi. Now that's the closest I can get this definition from calculus to the actual limit of x going to a. Right, and that would then be the slope. And we call this forward difference because from the grid point xi we go forward to larger x values. But equally valid would be to go backwards. If I'm interested in the slope at xi, I don't only have the only option of going to the plus side and taking the limit of coming from the plus side towards xi. I also would have the option from calculus of coming from the left side, so from the negative x direction. And there the closest point would be xi minus 1. And if I use the definition from calculus as this slope of the line that goes through these two function points, that would then be my approximation to the actual tangent line slope at xi. And because we go backwards in the negative x direction, this is called backward differences. Now you might have realized that one of these slopes, the backward differences, overestimates the slope at xi, and the other one underestimates it. So one idea one could have is, well, let me take the average of these two slopes. So let me take the point xi plus 1 and xi minus 1 and build a line through these 2 points and take the slope of these 2. So that would be the slope of the line that goes through xi plus 1 and f of xi minus 1. And because the point where we actually want to evaluate the slope, xi, sits in the middle at the center between xi plus 1 and xi minus 1, this approximation is called the central difference approximation. Okay, in this case, it looks like the central approximation would be the best approximation from the 3 that we have looked at so far. Thank you for watching.